Hi guys, welcome to the Chromatography Laboratory Experiment at Nazareth College. Chromatography is a physical method of separation or purification that allows you to separate components of a mixture in between two phases. One is the stationary phase, that is the one that doesn't move, and one is the mobile phase, and that is the one that has a definite direction. The eluent is the thing that elutes from the end of the column, and the eluent will contain your analyte. And the analyte is the thing that we're interested in this separation. We will be doing two types of chromatography today. The first will be thin layer chromatography, or TLC, and the second will be column chromatography. TLC can be used to monitor a reaction, looking at how much product is formed, how much starting material is left over. It starts with the stationary phase, which is a plate that is coated with silica gel. And then we have our mobile phase, which is a solvent, and in this case we're using 80% hexane, 20% ethyl acetate. So you place the solvent in the bottom of a beaker or developing chamber, and you place the TLC plate or the stationary phase vertically in the beaker. You spot your sample or your mixture at the bottom on the pencil line, and then you allow the mobile phase to travel up the plate using capillary action. Because the silica gel is very polar and the solvent is very nonpolar, your molecule will decide whether it prefers to be on the plate or in the mobile phase, and it will travel up the plate accordingly. Depending on the polarity of our analyte, it will spend time in both the mobile phase and the stationary phase, and ultimately be separated based on its polarity. Polar molecules prefer the silica gel and will stay on the plate lower, whereas nonpolar molecules will travel farther up because they prefer the mobile phase. The compounds that we will be separating in this experiment are ferrocene, shown here, and acetylferrocene, shown here, as well as a mixture of the two compounds, ferrocene and acetylferrocene, for a total of 3 spots. You will be given a TLC plate. 1 centimeter from the bottom, draw a pencil line, which is called your spotting line. Be careful not to disturb the silica gel when you are using the pencil. Transfer a small amount of each compound onto its own watch glass and dissolve all 3 in a small amount of mobile phase. It is now time to spot the TLC plate. We are going to be using these very thin capillary tubes for this purpose. Take a small amount of the sample on your capillary tube, place it on the X. Very careful. Okay? So then once you spot it, you can go back and recharge your capillary tube and respot it several times, as you can see here, placing it right on the center of that X, keeping track of which X is which sample. So this is our ferrocene. If you remember, I left my bottle set up so that I knew which spot was which. You could also write it in your notebook. So just continue to spot it. You let it dry in between each one. And this is so that we can actually make sure we get enough sample on the plate so that we can see it once it gets developed. Okay? So when you're all done spotting all 3 samples, this may be what it looks like. And now it's time to develop our TLC plate. Place it into a beaker with 0.5 centimeters of developing solvent. Remember, that's our ethyl acetate hexane mixture. And so you can see there I had a little slip up. My TLC plate slid down a little, but I think it still did not go above my spotting line, so I think I'm okay. Be sure to place your watch glass over the top of the developing chamber to keep the vapors inside for a saturated chamber. And so now we're in the developing chamber. I have fast forwarded this 8 times. The entire process took about 2 minutes. And so you can see the solvent moving up the TLC plate, and you can actually see the samples moving up as well because they have nice color. According to the experimental protocol, what did I do wrong here? Email me now for 1 point extra credit. Once the solvent line gets near the top of the TLC plate, we can remove it from the chamber and then quickly mark where the solvent front was. This solvent front line will become very important in our RF calculations. You can see the acetylferrocene spots here, but you can't really see the ferrocene spots. So we are going to use shortwave UV light, which allows us to visualize both the acetylferrocene, which I'm circling here, and the ferrocene, which is up at the top here, right by the solvent line. These compounds are visible under UV light because they are aromatic. So you want to carefully with a pencil circle all of those spots that you see under the UV light so that we can calculate our RF values. The reason there are two plates here is because I did this experiment in duplicate. You will be responsible for calculating the retention factor or the RF value for our compounds on this TLC plate. It will be included in the data portion of the Moodle course. The RF factor is a ratio that compares the movement of your compound compared to the solvent front, all from the spotting line or the origin, as shown in this diagram. There you have it, TLC. Now let's do some column chromatography. The basic theory of column chromatography is that the stationary phase is polar and the mobile phase is less polar. And once we load our sample at the top, it will spend its time either in the stationary phase or in the mobile phase. And as it goes down, the different compounds are going to interact with the two phases differently, and your two compounds will be separated or resolved. In this figure, the green band has a weaker interaction with the stationary phase, and therefore it spends more time in the mobile phase and will elute first. The orange has a stronger interaction with the stationary phase and will therefore be retained on the column longer. Okay, enough theory. Let's get into the lab. You will be given a column, a long glass column, that you will pack with silica gel. Check the stopcock to make sure that it's working. Pour the silica gel in from the top using a funnel and bring it to a total of 4 centimeters. Okay, that will be our polar stationary phase. Once we ensure the stopcock is in the closed position, we can begin adding our mobile phase, which is a mixture of hexanes. You will use a funnel and pour hexanes into the top of the column, almost to the top. Now we will open the stopcock and allow the mobile phase to run through the silica gel. You will collect this eluent in a beaker. You will see it does take some time for that mobile phase to move through the stationary phase. In the spirit of saving some time, I have fast forwarded this portion of the video. It originally took 2.5 minutes for the mobile phase to reach the bottom. It is crucial that you never allow the level of the hexane to drop below that of the silica gel at the top of the column. Yay, we have a drop. At this point, we are going to drain enough of the hexanes into the empty beaker until the level of the liquid in the column is about 5 millimeters above the top of the silica gel. I would like to reiterate that you are never allowed to let the column run dry. Never let the level of the liquid fall below the top of the silica gel. In this experiment, we will be using column chromatography to separate a mixture of ferrocene and acetylferrocene. Pre-weigh 2 Erlenmeyer flasks, 1A no label and 2B with a label, prior to starting. Weigh out 0.1 grams of the mixture of ferrocene acetylferrocene and apply it to the top of the column using a funnel. Now, using a pasture pipette, wash down any mixture that sticks to the funnel or to the walls of the column, being careful not to disturb the top of the column. You can tap the column to try to remove the air bubbles. Open the stopcock at the bottom. Allow the mixture to enter the column. Make sure that you replace hexane at the top at all times carefully so that you do not disturb the top of the column and so that the column does not run dry. You will be able to see that our ferrocene begins to enter the silica gel. And over time, you see the yellow band traveling even farther down the column, leaving the acetylferrocene behind. I took a video of the entire process, the full separation, and it is shown here. It will take about a minute for us to watch it, but it took me an hour and a half to film. So we will see that we're adding hexane at the top and we're watching the yellow bands come through the column. When it gets closer to the bottom, we will have to make the change and collect it into one of the pre-weighed Erlenmeyer flasks. You'll see that in just a second. There you go. This will be Erlenmeyer A. Okay, so now we'll transfer back to a regular beaker. This solvent that's being collected here is simply hexane. So we will add ethyl acetate as a solvent now, and you can see that the orange band comes through with the ethyl acetate. And as soon as the orange band gets close to the bottom, we'll switch to our Erlenmeyer flask and collect the second compound into that Erlenmeyer flask. This will be Erlenmeyer flask B. Both flasks were placed in the hood to evaporate the solvent over the next week. Once complete, I used air to push the silica gel out of the column and placed the used silica in the beaker in the waste hood. 1 week later, the solvent was completely gone, and so I weighed the contents of Erlenmeyer Flask A and the contents of Erlenmeyer Flask B for a percent recovery calculation. Additionally, I did a TLC analysis of the contents of Flask A, Flask B, and compared that with the mixture. I used short wave UV light, and I circled the visualized compounds on my TLC plate for RF analysis. Again, I did this in duplicate. We did it. We did chromatography with the column and with TLC. It might be interesting to compare the results we got from the TLC from part 1 and part 2 of this lab. And now, safety with Jane. But subbing in for Jane is the other Dr. C, Dr. J. Charlevoix.
This colorful lab does have a few safety precautions, which include: do not look directly into the UV light source used to visualize the TLC plates. The used capillary pipettes may be placed into labeled beakers around the lab and ultimately will be disposed of in the cardboard glass waste containers. Hexane and ethyl acetate are flammable. Therefore, please use caution when handling these mobile phase solvents. Dispose of all solutions and developing solvents in the organic liquid waste container in the waste hood. Place used silica gel into the waste hood in the beaker labeled silica waste. Not really a safety concern, but a general warning. Do not allow the level of the mobile phase to drop below the top of the silica gel. And there you go.
There you have it, chromatography. We did thin layer chromatography and column chromatography. Such a great way to separate components of a mixture based on polarity. All right, good luck.